So chapter 15, I just want to go through just a little bit about chapter 15 and give you some basic information on sinusoidal waveforms and how they're actually created and all that good stuff. So basically, what I want to do is put up a sinusoidal waveform here. Let's start with that. Let's just start with a general sinusoidal waveform. So we know the sinusoidal waveform looks something like that. So that's basically a sinusoidal waveform, and then we also have what we call the quadrant system. So let's get the quadrant system going here. So if we look at that, here's quadrant 1, here's quadrant 1, quadrant 2, 3, and 4. So quadrant 1, 2, 3, and 4. So we know that this is 90. This is 180. These are degrees. This is 270 and 360 degrees. So we know that if this generator, let's say a generator is running, we will actually have, we'll call this quadrants 1 and 2. And we'll call these quadrants 3 and 4. Quadrant 3 and 4. We know this has to be 0 degrees, and this is supposed to be over here. That's supposed to be 0 degrees. Here is 90. Here is 180. And here is 360 degrees. So if I actually want to do this in, radiance, in radian mode, I would actually have here. So if I was looking at this as in radian mode, I would actually have 0 radians. I would have pi over 2 radians. I would have pi over 2. I would have pi radians. And then I have 3 pi over 2. And then I would have 2 pi. So this is actually 2 pi. This is pi. So if we look at that, we can actually use pi in radian mode. And people have been asking me, what's the use for pi for radian mode? And when you actually use imaginary numbers, rectangular and polar, you will work in radians instead of degrees. So just keep that in mind. We're going to focus on degrees here, but I want to get a fundamental understanding of radians before we actually moving on. So basically, if we look at this in the book, in table 15-2 gives you a real good idea of how many degrees there are in a radian. So, and it breaks all those radians down for you. For example, 30 degrees is equal to pi over 6. And it's 50% of the maximum. And then we keep going through that. And that'll be important later on when we start talking about capacitors, when we start looking at the charge of a capacitor, et cetera, and inductor. So, but for now, let's look at something here. If we actually take and we want to know how, let's say we have that. And I'm going to break the circle down. I know it's not perfect, but I want to know how many degrees there is in 1 radian. How many degrees there is in 1 degree. So the number of degrees in 1 radian. 1 rad. Number of degrees in 1 radian. Well, we know that there is actually 360 degrees in a circle, so it's 360 degrees, and we can actually know that there's 2 pi radians that take up to make up a full waveform. So 360 to form 1 full waveform, and pi, well, degrees per radian. That gives us an understanding degrees per radian. So if we take 360 divided into 2 pi, we actually come up with 57.3. I do believe it's 57.3 degrees per radian. Well, it makes sense. This division right here is a ratio to the number of degrees per the radian. So we're just simplifying. We're simplifying it down. So it says there's 57.3 degrees per radian. So that's how you actually get the number of degrees per radian. All right. So in order to understand where I'm coming up with the 0.707, the radical 2's and all that, I would have to actually dig really deep into this, and I really don't have time to get into the true workings of the sinusoidal waveform here, but just give you an idea, not trying to water this down any more than I have, is remember that big circle I gave you? It gives you all the radians, and it actually gives you some polar and rectangular coordinate systems in it. But in short, if we actually take a look at this, RMS is about right here. So if we take the sine of 45 degrees, we get 0.707. So you can see that we can actually start breaking down. So that's 0 degrees, 45. So we're looking at right about here is 45, because that's 90 right here. So that's 45. So it's, I'm a little off. It's about right in here. Some places 45, and then you get 90, and then you keep bringing it up to 180. So basically, as you're going around the circle, you're starting at 0 degrees right here, and you keep going all the way to 180. So you're increasing and then decreasing back. You're actually increasing to 180, and then you're going to increase back to 360. So remember that big circle. So 45 degrees is about right in here someplace, right in there. So that is the long story short of where we're coming up with 0.707. And actually, we're coming up with radical 2 and all these other different equations. So let's take a look at this for a second. The average value is equal to 0.637 times the peak. Okay, so 0.637 times the peak. So our RMS, this is voltage, by the way, volts, 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 and volts. Volts RMS is 0.707 times peak, and then our peak voltage is 1.414 times RMS, and our peak to peak is 2 times the peak. I did a lecture video on the sinusoidal waveform using multisim, so I'm hoping this ties everything together. So when we talk about frequency, frequency measured in hertz. So how do we get hertz? Well, it is 1 over the time. So how do we come up with time? On our oscilloscope and on this graph here, time is on the x-axis and amplitude is on your y. So what we can actually do is, if I actually put down something, let's say I take, let's do this. I come here and I do this. Remember, I'm measuring one cycle. How long does it take to go one cycle? So if I measure from this point to this point, and that's 360 degrees or 2 pi, I get the time. And we have these divisions on here, these vertical divisions that are on the oscilloscope. We can actually measure that time. We can actually measure that time. So if I ask you for frequency, I have to give you time. Likewise, I can find the time on here. If I give you frequency, time would be then 1 over the frequency. This time is equal to 1 over the frequency. So again, frequency and time are easy to find if you have one of the values. So just remember, to get frequency, you take 1 over time. If you get time, you take 1 over the frequency. Frequency is measured in hertz, and that is a German gentleman who actually came up with some of this great information. So when we look at frequency of time, we're actually talking about the period. Well, period then would be one complete cycle. So remember, a sinusoidal waveform is just a repetitive pattern of sinusoidal waveforms that are just grouped together. That's what we see on an oscilloscope. So a period is equal to the time it takes to make one cycle. So that's the definition of period. Period is equal to the number of time it takes for one cycle to occur. So we now want to talk about wavelength. Wavelength, definition of wavelength, is a distance traveled by the wave in one cycle. We already know what a cycle is. We already discussed that. So to get the wavelength, and we consider this special symbol called lambda. Lambda is equal to the velocity divided into frequency. So velocity divided into frequency. So when we talk about velocity from physics, maybe take some high school physics, maybe some college physics, we know that velocity is a distance over time. It is distance, the measurement of velocity. If you know the distance, you know time, you can actually get velocity. So velocity is a measured value, which it does have 2 components, a distance and a time. Since velocity has 2 components, we know that it has to have units, right? So this case, distance, we usually use we'll use centimeters here. centimeters per, and time's always in seconds or milliseconds, but it's in centimeters per second. Centimeters per second is velocity. So you got centimeters per second for the velocity, and frequency is hertz. So what we have here is the units for wavelength, or lambda, is going to be centimeters per second per hertz. So it's going to be centimeters per second per hertz. So is the units.